today we talk about matching game. And here's the overview again. And here's the outline. And we have the motivation about future network and the distributed solution. Then we talk about the matching theory, game theory kind of basic. And then we talk about this kind of, this applications in various applications. And typically, okay, when we talk about matching, there are two things. And one thing is about this matching, this combinatorial matching. So in this case, okay, you have this kind of one pair to match the other. And then, okay, in this case, you do this kind of centralized matching. And then the algorithm is typically called Hungarian method or H matching. But the complexity is O(n) to the power of 3 or O(n) to the power of 4. So that complexity is very high, even though it can achieve this kind of centralized solution. Centralized optimized solution. Here we discuss about another one, which is matching game. So basically here the complexity is O(n), so linear complexity. As a matter of fact, it's much lower than that. But let's see what we can do. And first, for future network and for 5G network, they need a lot of devices and rich communication content. And for 5G feature, they need high data rate, capacity, reduce the end-to-end, high energy efficiency, better network coverage, and enhance user experience. So for 5G technology, unlike this kind of 2G, 4G, and 2G, 3G, and 4G, there is a distinct kind of technology. In 5G, it's more like a buffet. For example, D2D, and then okay, SDN, LTE, and all these small cell, and all these type of small things combined together, such that they can achieve this 5G requirement. And so basically, okay, there are all kinds of network virtualization, C-RAN, mapping MIMO, Internet of Things. So 5G is more like a buffet. Okay. And for 5G, then this calls a 5G challenge because you can have all kinds of different type of communication. They have the very much kind of heterogeneous character. And also, sometimes you have ultra-dense network, especially for IoT, and mobile mobility management. And for centralized solution, okay, you need global information, so you need to gather all the information. And you need a significant overhead. So in order to do the resource allocation better, I need to collect all the information. So those information is impossible to collect. And the network management complexity will be extremely high. As I mentioned, this, for this case, for matching case, if you do centralized, the complexity is O(n) to the power 3 or 4. So, and also with very high latency, because the communication, I send the instruction to the central point, then the central point give me an instruction. So this round trip delay, okay, cause high latency. So we need to shift from the centralized one to the distributed one, especially in the future. Okay. So let's give us a motivation. And as I mentioned, okay, for game theories, try to have this distributed solution. And there are many different ways to do that. And today we talk about matching game. So let's say, what is a matching game? So the basic story is that, okay, the matching game starting from the dating, okay. A group of men try to date a group of women. And then the goal is to find everybody a date, such that, okay, they can get married. And we want to prevent the unstable marriage. And this is the original goal for that. And similar to us here, okay, we can have user and resources, and how could we match them together? So basically, this is a kind of goal. And then, okay, so this is the goal is how to design a very low linear complexity algorithm, such that we can achieve stable result, and also the solution is near optimal. So basically, this is the goal for that. Okay, and the founder of this one is Shapley, and also the Ross. They both won the Nobel Prize 2012 for matching theory. So basically, let's try to study what they are proposed. So the definition. So in economic, matching is a mathematical framework attempt to describe the formation of mutual benefit relation over time. So basically means who should work with whom, or this thing match to the resources. This user match to these resources, something like that. But for matching theory, you have a graph, and where this kind of, we try to match this kind of a user with a different player. So let's say, okay, the basic element. So here we give a simple example, which is a stable marriage. And we have an agent. We have two sides. One side is man, the other side is woman. And then, okay, we have a preference list. So for man, okay, you want to date in your man, what is your goddess? And then what is the next one? And you have a list, right? And so basically in your man, you have this. And then, okay, for ladies, okay, you have a beautiful, handsome guy, and you have a spare tires. Oh, sorry, okay. This is spare tire, is by the word. Okay. And then, okay, you have a list, right? So basically, everybody have a list for this one. And then, okay, for the blocking pair. So what does mean blocking pair? So the basic thing, a man is unhappy with his wife, but is happy with the other guy's wife. And the other guy's guy is happy with this guy, that is her husband. And then what happens? These two couples just kind of divorce, and this man marry that woman, right? So this is an unstable marriage, which we don't want to happen. So this is basically, okay, we want to have a matching such that we don't have the unhappy marriage, this blocking pair. So this is the goal. And then this is stepping goal. We want to have a matching without this one. And the Gale-Sharpe algorithm is to such kind of algorithm to find this kind of stable marriage. And pay attention, okay, this algorithm is trying to find the stable marriage, not the optimal solution. But the solution is typically near optimal in the sense that, okay, you always want the people on top of your list, right? Even though sometimes it's not approachable, but you're always looking at the best or the better one. So in this case, the solution, even though it's not global optimal, it must be near optimal. So let's see the solution, okay. So this is GS algorithm. We have a set of man and set of woman. And then the man have the preference list. So item like guitar better than high key, better than Irina, better than Frank. And obviously, okay, he tried to date guitar. And guitar say yes, okay. And then Bob have his preference list and try to date Irina on the top of the list. And the cars also have like guitar. And then try to PK with Adam. And guitar think, car is taller, richer, and handsomer, and then done Adam. Okay. And then Adam have to find the second on the list, which is Hita. And then David do the same story. And anyway, so finally, okay, this is a kind of very simple solution. And then finally, this is a converged solution. There's no guy want to kind of no unstable marriage, and there's no blocking pair here. So you can see such kind of algorithm is a very simple algorithm, and the complexity is O(n). As a matter of fact, it's much lower than O(n). Why? The reason is okay. I only need to date the girl that I have interest. I don't need to have the preference list of 3.5 billion women, right? I don't need to have that preference list. So even though the complexity is O(n), as a matter of fact, it's much smaller, right? So basically, and also such kind of solution is stable and also near optimal. Okay, later we will show for that. And so here you can show the performance if you try to implement such kind of matching game, and in this kind of performance curve, you can use the H matching or Hungarian method to have a centralized solution. And then, okay, you do this kind of performance analysis and then compare with this one, you can show that the performance gap is very small. But this is distributed and low complexity. And why this matching is very popular? In the sense that, okay, typically the assignment problem is difficult. So integral part is difficult. So to this one, who should work with whom? This is the integral programming part. It's much more difficult. And after this integral programming is done, within the pair, they do some kind of power allocation or this continuous variable resource allocation. It's relatively another story. It's a convex optimization. So basically, this is the story. Okay, so this is the basic definition, and let's see about classification. And for classification, okay, you have a different way. First one is a one-to-one matching. And for example, stable marriage is one-to-one matching. Okay, except you are in Saudi Arabia, one matching 4, typically one-to-one. And believe me, one is more than enough. I'm just joking. And so this is stable marriage, stable roommate, and basically, okay, for roommate, sometimes in United States, it's only 2. So it's a stable room, 2 people share the room. So it's also a kind of one-to-one. Many-to-one. So for example, house student admission. So everybody want to go to Harvard and MIT, right? But Harvard and MIT have the quota. How many people they can admit? So in this case, okay, and many people want to go to there, but they have quota. So this is many-to-one. And they have the money-to-money. For example, worker and firm. After graduation, there are multiple firms try to hire and multiple students how to match them. And also, assign paper to reviewer. For example, now if you submit a paper to Infocom, they have the algorithm there to, according to your previous submission, they allocate you to this kind of the reviewer to the paper. And you have multiple paper, multiple reviewer. So basically, how you allocate them each other. So it's a matching to matching. Okay. And another set classification is that okay. Type of classification is that okay. You have this bi-party matching. So basically, you have 2 sides. So both sides have the preference. For example, stable marriage. You have your preference to ladies, and ladies have preference to you as well. And junior doctors to hospital. The doctor. In United States, doctors need to go to hospital for several years before they can start their own business. So the doctor want to go to some good one like Johns Hopkins, Andy Anderson, but on the other hand, this hospital want to select the best one. So also it's a kind of a two-side matching. And sometimes you have one-side matching. For example, campus house allocation. You have a preference to go to this kind of different campus, different kind of house, but the house have no preference to you, right? As long as you are not criminal, right? So different people, okay, the house have no preference. And then finally, there's no bi-party. So basically, okay, there's no preference in either side. For example, for P2P network and from the chess tournament. So in this case, they don't have the preference in both sides. So there's another classification. Classification 3 is that okay, the matching without eternal effect. And suppose so this one means okay, the others matching will not, matching result will not affect your preference list. Okay, so this is okay. And on the other hand, there's a matching with external effect. For example, you have your goddess, and your goddess just get married. So your goddess still on your top of the preference list, you probably get rid of it. The change to another, the preference list change because the other kind of a matching result, right? So in this case, okay, it's a matching with the external effect. So pay attention to this one. This one is important. And typically, okay, for some application, is without external effect. Some application like interference channel. This channel is good, but if this channel is assigned by the other user, this channel might be not good for me anymore. So basically, external effect need to be considered. And there's another kind of, classification, matching without transfer. So no transaction between the two agents. And matching with the transfer. That means the transaction between the matching agent, like the money, credit, like the spectrum trading, and something like that. So basically, okay, in other words, when you get married, it's a free marriage, that is without transfer. Or you have to pay a lot, that is with transfer, okay. So basically, okay, this is a 4 different classifications. And then let's talk about 4 different examples. 4 different examples, and then with a different kind of situation. And let's have the hospital resident. So for United States, okay, the basic thing is that, okay, for the doctor, after graduation from the medical school, they will go to the hospital. And then they have a set of resident doctor and set of hospital. And the hospital has the capacity restriction. So MD Anderson can access only a few limited amount. And then it's a generalized GS algorithm. And so basically, okay, so basically, this is a more, this is typically using this rural hospital theorem. So basic story is that, okay, this is a more generalized than this kind of stable marriage. In the sense, okay, stable marriage, you can only, one man can only marry one woman, right? And here, one hospital can admit it into the multiple kind of residents, but then this multiple resident, okay, the hospital has a limitation, okay. Okay, and the hospital resident and have virus. And this is one type of virus, so this called 3-gender problem. And so basic story is that, okay, here, instead of 2 parties, they have 3 parties. And this story is that, okay, man prefer woman, and the woman prefer dogs. So what you can do here? And then, well, we presented this one to the National Science Foundation. And then, okay, the program manager is lady, and he sounds to be very happy, so we got it funded. I'm just joking. And so we have a strict order over the different pair, and then how could we prefer over the individual agent? And another variation is the house resident with couples. So basically, this is a 2-party problem. Okay, for example, the two couples want to allocate to the same hospital, and yeah, this is in US, the academic, there's such kind of problem. In the sense that, okay, there are the couple all get high degree, and then the university want to have one of them. But how about the other? Sometimes the university is in the middle of nowhere, and then, okay, the other is a trouble. So basically, this one is such kind of problem. And the mapping worker with firms. So there's basically, okay, so this is a many-to-many worker, and then you have the many worker and many firms, and then each firm have this kind of, limitation, and each worker try to match to them. And the difference here is that, okay, for this type of many-to-many matching, there might be a kind of cyclic case, so that, okay, the stable matching might not exist. So basically, this one, and also they have the individual and the group preference. So a group of people have the preference. So there are some kind of variation here as well. And that is the first type. And the second type is a house allocation. So for the hospital resident, the hospital has the preference to the resident doctor. But for house allocation, the resident has the preference to the different apartments, different house, but the house have no kind of a preference to the resident. So that is a one-sided, kind of preference case. So the house has a capacity of limitation. So we have this different priority optimality, like the Pareto optimal. So in other words, okay, no applicant can be better off without let the other suffer. And also they have this different definition, like the popularity profile-based optimal. So popular means that matching is popular if there's no other matching that is preferred by the majority of the appliance. And there are other kind of optimal concept, like the profile-based optimal. So satisfy certain condition of agents ranking of their partners. So basically, okay, in this case, there will be other type of kind of optimality things here. And then there are some kind of variation. So basically, reviewer assignment problem. And so basically, okay, the story is that, okay, reviewer, okay, and each paper, every time you submit a paper, the paper needs at least 3 reviewers, right? And it's typically the case. And then the reviewer have the preference on which paper to review. Sometimes I don't accept the review because I have no idea about that paper. And but the paper have no preference on you. But the paper have this kind of requirement for this three reviews. So basically, this is the case. Okay. And anyway, so and this reviewer's assignment problem. Then the reviewer interest and expertise, they have the conflict of interest, and also they have this load balance and coverage constraint. And the solution technique is basically okay for different. They have heuristic, approximation algorithm, integral programming, whatever. So Professor Bao Chunli in University of Toronto, implement the algorithm in EDAS, such that okay, when you submit some of the conference, like InfoCom, and your paper is assigned automatically by the system. So that is a good thing, in the sense. It's based on the matching, and other some heuristic. But the problem for matching is that okay, I asked him, because you have many to many, if you pure using matching, might not be stable, might not find a solution. Only 1-to-1 and many-to-1 have this kind of stable solution. But many-to-many might not have. So I asked about Chunli, okay, what is your trick? He said that this is a patent, and he wants to keep it a secret. I don't know. I don't know. Okay. And there's a called Lysimin optimal matching. So maximize the profile of the worst of reviewer, and so that maintain the fairness. Anyway, so such kind of problem have a kind of a different certain solution. And the third one is a stable roommate solution. So let me go back a little bit. So give me one thing. Okay, let me remember. For stable roommate, basically, okay, you don't have this party. So the difference is that for the house allocation and the house resident, you have two party, and or it's a stable marriage, you have male or female. But stable roommate, you don't have. So everybody can share together. So you only have one party. So in this case, what is the solution? So the basic is set of students looking for roommate is 1-to-1 pair. And how many kind of, when I was an undergraduate student, there are 6 students per dorm, per room. And in the United States, it's 1-to-1. And I don't know how about in Korea. I don't know. Anyway, so this is a 1-to-1 pair, okay, in this case. And they have a stability. The stable matching may not exist. And so the algorithm is called Irwin algorithm, or Tan, I don't know how to pronounce it, algorithm. And so basically, okay, in the stable roommate problem, there's only one type, one side, and then they want to each side each side, we want each person have the preference on their roommate. And how could we find that such that, okay, everybody's happy, so they will not fight within the door. So this is basic idea. So there are different variations. They have a stable crew. And in this stable crew, okay, for example, there's pilot and co-pilot. And in this one, there's only one difference is that, okay, they have the role of pilot and co-pilot. And even though otherwise it's the same, they have the stable fixture. So basically it means, okay, we have a size of player for the chess and a size of player chess. We want to allocate them such that, okay, for example, you have 100 gamer, but each one will only play maybe 10 games. Otherwise, too long, right? So how could you rank them? Such that I will play with the player with a similar level to me. I don't want to play with, this kind of IBM machine or with this world champion. And the world champion don't want to play with me, right? So we want to play with a similar level. So this is called stable fixture. That means we have a size of player and we have a limited number of games. So how could we make them most happy for this assignment of the different players? And then they have a stable activity and a stable multiple activity. In this case, in addition to game, in addition to chess, you may play all kinds of different things. And then, but you have limited number of time, and also limited number of rounds. So basically, how can you match them so that everybody is most happy? So this is, of course, different variation. And finally, the assignment game. So basically, okay, the story is that, okay, we have a set of resources and a set of a set of people and a set of resources. And then how could we find this kind of assign? Which one will assign to which resources? And so there are two-sided, assignment game. Buyer and seller market. Seller want to own one product, and buyer want to seek for the one product. And they exchange by the money. And they basically, such kind of problem can be formulated by linear programming. And then they can have a distributed solution to reach the competitive equilibrium. Okay. So basically, this is a kind of, assignment game, sorry. Okay. And so, in other words, okay, let me recap a little bit, because here, okay, in order to define the game, you need to define, the agent, typically two-sided or one-sided. And then you have a preference list. And here, okay, the good thing for preference list is that, okay, everybody want to have this utility maximization. So in other words, okay, you can define the preference list as your utility function. But preference list will be easier than this kind of utility function in the sense that, okay, you have to write down the utility function. But the preference list can make it more relaxed. So I prefer Samsung than iPhone. Okay, why? I have no idea. I'm in Korea, right? I'm just joking, okay. So basically, okay, I cannot quantify it, right? I cannot quantify. So there are many things that you cannot quantify. And in this case, okay, you do this kind of preference list. And another joke is that, okay, for example, okay, for guys, okay, this is a trick, okay. For example, your girlfriend asks you, okay, why you love me? You know that if he asks this question, no matter how, you're dead. Why? Because you answer the question, you are beautiful. Then she will think, you say, I'm not smart. And you say, okay, you are smart, I'm not beautiful. So no matter which way. And also you say it's 50%, 50%. Why not 30, 70%? So no matter how you design utility function, you are doomed. So what you can do, okay, you say in this way, okay, among my preference list, you are on the top one. So that's good enough. Okay, how you define it, I I don't care. Okay, so this is basically the trick. So in other words, okay, this preference list will give you a much flexibility on how to design things. You don't need to design a utility function, and you can design this kind of a preference list for that. And the second thing is that, okay, this is a stable marriage. They find a stable one, such as, okay, I mean, this stable one will always achieve near optimal. And also the complexity, okay, even though your preference list might not be a complete list, you can have a very short list. And for example, for any mobile, you only have the preference list around and related people. You don't need to have the preference list for to the resources which is relevant. So in this case, the complexity is low. And then the algorithm is always a generalized, I mean, kind of GS algorithm. So they have many variations, but this is very basic. You have this preference list, you try to date, and then you have preference list, you have try to date, you have preference list, and the other side also have the preference list, and then just kind of them or something like that, and then finally, okay. Yeah. So I have my student, and sometimes, okay, for example, I travel here to Korea for 2 weeks, and then when I go back, I would see that, okay, their kind of matching order, I mean, pair has been changed. And it's typical of that. But anyway, finally they found a stable one. So the good thing is that, okay, the convergence is very quick to the stable one. Anyway, so this is the recap for this one, and let's go to the application. Okay, for application, and so we want to have the users and the resources as an agent, and the users, obviously users have the preference list. The resources can or cannot, or may not have the preference list. Depend. Okay, and then we have the QoS requirement, which basically can be quantified as the preference list. But sometimes, okay, the QoS requirement can be multiple objective. In this multiple objective, you can use the fuzzy logic and then put into the preference list. So in other words, the preference list can handle the multi-objective function. And then system objective, and in addition to the, I mean, here compared with the centralized solution is a social optimal. And here for the game, it's a stability, or sometimes popularity optimal, Pareto optimal. So, but because everybody wants the one that's on the top of the preference list, so even though you only achieve stability, you are near optimal. And also the solution is very distributed and very low complexity, ON complexity. As a matter of much lower than ON. And the advantage, you don't require, for the game theory, you don't require others action. You have two-sided stability, and not necessary, no kind of utility function is needed, only this preference list. And also the second part, two-sided stability. For the centralized solution, it's not a stable solution, even though it's social optimal, right? And it's a bad joke, okay? During this kind of extreme kind of many years ago communist to assign husband and wife in a centralized way, right? Maybe okay in the extreme case, but that one is typically not stable, right? So basically, this is a kind of stability thing. And the centralized solution optimization, and basically we want to compare with this one. So this distributed solution will be a very, fast deployment. And we talk about different applications, and this kind of RTU, D2D, physical layer security, social caching, and RTE was in the vehicular network. So let's talk about the RTE unlicensed. So for RTE unlicensed, traditionally, okay, this Wi-Fi and this kind of RTE, the cell phone network using the different spectrum. And then, okay, this Wi-Fi is typically gets the indoor business, and the LTE gets the outdoor or the mobility one. And then, okay, it sounds like, okay, for more and more traffic is indoor, you download indoor. So the LTE is losing their business. And also FCC think, okay, for Wi-Fi and this LTE, and there are two camps. They want to introduce competition between the Wi-Fi and the cell phone network, so that it's better for the customer. So what they do is that, okay, let's introduce a spectrum, include unlicensed spectrum in 3.5G, I think so, or 3.G. I mean, I forgot exactly the number, such that both LTE and Wi-Fi can use. So they introduce a battleground, such that these two camps will kind of compete with each other, so that it will be better for this business, better for the consumer. So this is where the LTE unlicensed comes from. So the FCC give a spectrum that both cell phone user and Wi-Fi can use. And then here they need some kind of carrier aggregation to put the different transmission into the different spectrum to transmit. And they have the better performance, network performance, unified network management, and enhanced user performance. So the basic story is that, okay, we have a different base station, we have the unlicensed spectrum, and then, okay, how they can match together for this one. So different people have the different base station, because the location is different, they have the different kind of available spectrum, and then how can they attract this kind of users? So there's a kind of coexistence issues. So here, okay, we have this cell phone user and the unlicensed user, and basically, okay, for this the impact of cell phone user to the unlicensed user. Firstly, the cell phone user in the unlicensed one have to listen before talk. So if the unlicensed user, like the Wi-Fi user, is transmit, the cell phone user have to kind of be nice to them. And for the impact of unlicensed user to the cell phone user, they want to minimize the signal to, they want to achieve the minimum requirement of signal to interference loss ratio for the cell phone user. And so the impact of cell phone user to the other cell phone user, they want to avoid the cell phone to cell phone user, and so that, okay, if there are more cell phone user, then, okay, the unlicensed spectrum will be shared. So in this case, they will have this external effect for matching. So in other words, we have these resources, this spectrum, and which can match into this kind of unlicensed user and then cell phone user. And if more cell phone user and unlicensed user is there, this channel will become crowded. And then in this case, okay, the channel will be not good. So in other words, we have the external effect on this case. So this channel, by the user's preference list for this channel will be affected by the other user's kind of action. So in this case, you have this kind of external effect. So here we use a student project allocation protocol. So we have a cell phone user as a student, and unlicensed this kind of unlicensed user as a project, and the base station as a lecture. So basically, okay, we try to have the acceptance list. So basically, okay, the student propose and different project, and say, okay, the student want to have a certain project, and the lecturer to think whether or not it's good or not. So basically, okay, the student in here, the student or the cell phone user try to say, okay, I want to coexist with the unlicensed user, Wi-Fi user, and then the base station will try to judge whether or not such kind of things will satisfy this minimum requirement, or the Wi-Fi user has this kind of the performance they are not affected. So basically this thing. And then we have the preference list of this cell phone user to this kind of unlicensed user, which is a capacity. And on the other hand, this kind of preference of base station over this one. So the base station also have this kind of the lecture have this this kind of preference. This preference is a combination of cell phone user and unlicensed user. And then we have the student project allocation to find the stable one. So in other words, okay, here the story is that okay, this cell phone user and this unlicensed user have this kind of matching. But on the other hand, on the top, we have this kind of lecture to make sure that the overall performance is better or some constraint. If you can also add some constraint here to make sure that okay, the system performance is good. Otherwise, the matching might not be this kind of the best solution. So basically here you have a judge to maintain the network performance and the system kind of a minimum requirement. So basically, we initial from this, the student propose, and then let the lecturer make a decision to say, okay, to make a decision to say whether or not it's good or not. And so basically, okay, then after that they check if every student is matched. If yes, they just stop. Otherwise, they try to check if every student's matching is empty. Otherwise, they will propose again. And so basically, this iteration continue until all these kind of student requirement is kind of reached. So finally, they have a stable matching. So here, they have a dummy. Here, remember that there are a dummy kind of project. That means this user is not matching with anybody. So by doing this, they can make sure, the system finally can converge. So stability is only guaranteed conventional case. The TDMA bring this kind of, external effect. So the question is how to transform the matching into a stable again. So basically, okay. So here, the story is that, okay, this one is highly determined on who is kind of proposed first, right? And this has the external effect. For example, okay, let's give you an example. And well, let's say, okay, this is with external effect. For example, okay, there are the preference list on your top. There's a beautiful lady, preference on the last. But this beautiful lady kind of, whoever dates first will have the advantage, right? And then after marriage, this lady is, is get rid of from your preference list. This is the preference list, even though that, okay, maybe you are the better choice. So in this case, okay, this is happens here with the external one. So the question is that, okay, how could we, do, that is for marriage, but for resource allocation, we want to prevent such things from happening. And then what we can do to improve this kind of better performance. And another example is that, okay, for single cell, okay, resource allocation. And because for single cell, the interference is very severe. And if you draw, so if you draw the capacity region for a single cell case, it have a very severe interference. So you have C1 and C2, which basically, okay, the interference looks like this. And in this case, in order to optimize the capacity, and whoever comes first, whenever I occupy this channel, the other look at this channel because of interference. Well, when it comes in, it will not improve the performance. So in this case, okay, whoever comes first, no matter whether or not this user is the best to fit this one, it is the case. So for such kind of matching, it has a problem of this one. So it might not, it will reach a very poor kind of local optimal. So in this case, we need to have this inter-channel cooperation. So basically, we want to have the stable one, and also we want to have the Pareto optimal, and then in this case, we will have this kind of exchange. So basically, okay, sometimes due to the mobility, sometimes okay, due to the performance, we can exchange this kind of channel. For example, if this user is in this channel, the other user is the other channel, and we found the performance is not good or sometimes it's not stable, we swap. So how about you use this channel, you use the other channel, and then in this case it will be more stable and more kind of performance better. So here there's a systematic way to swap this kind of matching, and in this case it's called inter-channel cooperation, ICC algorithm. And then this convergence, every time it will improve because only swap. When you swap, only the performance is better, I will keep there. Otherwise, I keep original one. So in this convergence, it will converge, but not necessarily to this kind of global one, because it still have local optimal. Okay, but every time it will improve the performance. So here, this swap idea is typically used in this kind of performance improvement over this kind of matching with the external effect, because matching this external effect exists such that the performance might not be optimal, might not be near optimal. So in this case, you need such kind of swap solution to improve the performance one by one. Okay, here is the performance evaluation. This is the user's throughput, and here is this kind of thing. So you can see that, okay, here, this is the optimal solution by using this kind of centralized solution, and this is your proposed one, and this is a victim algorithm. So you can see that, okay, the performance is always kind of improved. So basically, okay, throughput comparison, and okay. This one means, okay, I don't swap. I only have one kind of one performance, matching ones. So matching ones, due to the case that, okay, the first comer will take advantage. So it might not be optimal. So if you swap a little bit, and then the performance can be improved and near optimal. So basically, this is a kind of a performance evaluation. And the second work is this kind of dynamic stability. So here, this user will have this kind of mobile. So in this case, okay, the performance will need to have the stable. So in this case means, okay, well, when we do the matching, it may be optimal, but things change, right? Things change, and then network dynamic, and at this time I have this preference, and in the next time my preference is change. So in this case, should we redo the GS algorithm or not? So even though the GS algorithm is very simple, but if your network size is much bigger, it might not be a good idea to redo the GS algorithm again. So in this case, what we need to do? So this thing is called RVV algorithm. So basically, okay, the basic idea is the divorcing and the remarriaging operation. So we select the pair that is not very happy due to the dynamic, and then we force them to kind of divorce and remarriage. And then here we have the many to one situation for this specific situation, and the algorithm is called RPTS. And compare with the repeating GS algorithm, we make use of the previous matching. So the previous matching, the majority of this matching is still stable. You don't need to do that. Only the people with a very high mobility, such as their preference list change a lot, then we discussing about the divorcing and remarriage. And so when we do this matching, we only do a partially of the matching. We don't need to do the GS algorithm again. So this is the basic story of the RVB algorithm, and it can reduce the complexity a lot. So in this case, so when you do this kind of, dynamic, you don't want to do the GS algorithm all the time, then you think about the RVB algorithm. And when you think about the external effect, then you think about ICC algorithm. Okay, this is the all variation of GS algorithm. And the third example we want to talk is about D2D communication. And we have a D2D communication, and then we want to matching the D2D communication with the cell phone user, such as this kind of performance can be the network performance improved, and also the interference will not be will be low enough. So this one typically you can use the GS algorithm, very straightforward to matching this kind of D2D user to cell phone user. But here we want to do a little bit, different. Suppose, okay, here when you report this preference list to this kind of matching, you always, until now, you always represent the true value. So I really prefer this girl to the other. Is that optimal? And can I lie to my preference list by telling the other my preference list is different? And then that is the story that we want to talk here. So how about you do a cheating on the preference list? What gain you can have? And here what we do is that, okay, we achieve better partner by falsifying the preference list. We are cheating on this kind of preference list. And then we form a cabal. So a group of men prefer each other's preference list to its own. So basically, a group of men, when you form a kind of, it's called cabal, and then you try to falsify your preference list. And then a group of men who would otherwise prevent the cabal from getting their desired partner. And then the story is that, okay, if a cabal exists, then each man in the cabal can be strictly better off. So so basically, okay, if you can, inside the cabal to cheat on their preference list, the payoff can be no worse than not cheating. And it cannot guarantee that you get your better partner, but okay, at least it's not worse. It's not worse off. So this is basically the cabal thing. And then there are some algorithm about variation about GS algorithm. And this one is in a JSAC paper by my student. And then the next story is that we want to talk about is the physical layer security. And for physical layer security, we form the source and the jammer and decide the mandatory kind of compensation. Oh, by the way, okay, let me tell you the story, okay. So for physical layer security, okay, we have the source to send to the destination, and then, okay, there's an eavesdropper nearby. So what we can do, such as we transmit the information, such as the eavesdropper gets 0 information. So typically what they do is that, okay, they do this kind of coding, such as the capacity equal to from the source to the destination minus from source to the eavesdropper. And then they can do the coding, such as the eavesdropper gets 0. But in addition to that, okay, I can hire the jammer next to the eavesdropper, such as, okay, to jamming the eavesdropper. Even though they are the jammer in the information, it also kind of affect the destination. But the capacity from the source to the destination will degrade. But the capacity from the source to the eavesdropper will degrade much faster because of jammer. So in this case, the capacity, the sequence capacity from which is equal to from the source to the destination minus from the source to the eavesdropper will increase. So this is the basic idea why we want to hire the jammer. And the story is like this. 2005, I was in Cyprus and for a conference, and I have a friend and want to date a girl. And he talked to me. I said, "It's your business, nothing to me. Why you bother me?" And he said that, okay, unfortunately, this girl's boyfriend is on the same table. So you see, this guy is a source. This girl is a destination. Her boyfriend is an eavesdropper. And then he asked me, how could we solve such kind of problem? And I say, I become a jammer. So I sit next to the boyfriend, try to talk with him for Eurocup, for soccer. So distract kind of the boyfriend, so that my friend can talk with the girl secretly. And then after that, we think, I need to get paid, right? So I charge my friend with the dinner. You have to pay my dinner. Anyway, so after that, we publish a paper, the physical layer security game, how to date a girl with her boyfriend on the same table. It's a real title of the paper, and it's very highly cited. Anyway, so basically this is the story, okay. And then we want to, here, that is a one-part case. And here, suppose we have multiple source to destination and multiple kind of eavesdropper and multiple jammer. So how could we match them? Who should I hire? For example, okay, this is an eavesdropper. I would hire the friend next to it. I don't want to hire the friend far away, right, or to my destination. That doesn't make sense. So who should I hire? Okay, so this is a assignment problem. And each jammer makes the price offer to the source. The source proposes to the best jammer, and jammer decide to accept or increase their certain amount and terminate with no offer. And finally, we have the competition equilibrium. And so this is basically kind of jam. For this matching, okay, the price will be changed a little bit. So previously, they don't have the price constant. So this matching involves a little bit of auction, which we discussed yesterday. Okay, for social caching. So we have this social caching, and this is a many-to-many caching. For example, for this user, and then we have this small base station, and then we have this kind of service provider. So basically, and they have this preference list for the delay, popularity, and then how could we match this content, different content, into the different base station, such as, okay, we have the user can satisfy. And here, we write a kind of paper. We got this 2016, this presidential election Twitter data. And after the Twitter data, we try to analyze using the deep learning for this preference. So basically, after analyze the Twitter, we will know that you pro-Trump or pro-Hillary by using your Twitter. And then because the Twitter will to the local base station, and we analyze just right there. And then we, for example, on campus, people are very left, right? Revolution, okay. So in this case, when we analyze this Twitter result, it's probably very pro-Hillary. And in this case, we do the matching so that, okay, for the content, we match CNN, MSNBC, all these left media to the campus base station, this matching. On the other hand, I live in a rural area. It's cheaper, or it's a redneck. And then when we look at the Twitter, they probably pro-Trump. So we cache the false news and the right-wing news to the local base station. So by doing this, the delay is reduced, right? So basically, this is kind of social matching for this. And so this is related to deep learning. I will talk about deep learning and the game in the deep learning tomorrow, due to your assignment. Okay. Okay. Anyway, so another thing is okay, RTE assists vehicular communication. So basically, we have a LTE assisted with AO211p. So for Wi-Fi 1, the problem is that the access is very slow, and the other thing is that it's uncontrollable. So LTEV is basically more popular, especially with Huawei is pushing the LTEV. So basically, for your mobile, it now can be mobile on the car or in the UAV. There are a lot of papers for UAV which moving around and serving as a kind of base station. And so basically, they can have a safety critical application, better reliable, low latency, and more efficient. So basically, you need to have optimized the content sharing and data class diversity communication link. So here, we use a stable fixture model. So each base station has a limitation, and then they have multiple decisions. So for different tasks, how could you face them? So we form the coalition formation, the different cluster, and then we flexible for many-to-many matching. So here, this part we use a stable fixture combined with the coalition game, which I talked yesterday, and so we can have this kind of matching together. So this matching, can fit into this kind of different situation. And the conclusion is that matching theory model a suitable model for specific issue, and this is typically a assignment problem. And then they have the preference list, which is very flexible, and then they achieve stable stability of their goal, even though it's not social optimal, but it's typically near social optimal. And very efficient and distributed algorithm, because the preference list, you would only date the girl nearby, right? You will not have a preference list of a very long preference list. And it's close to optimal solution. So the wise choice for resource allocation, and because combinatorial, as I mentioned, the resource allocation in the future network is a mixed integral programming. And the integral part is typically making it NP hard. And here, using this kind of matching one, you can make this one much simple for the integral part. For the rest, you use the combined optimization. And moreover, this matching can be combined with many different other stories. And you can combine with this one with learning, with a correlation game, many things. And then there are many applications recently for this kind of different scenario. And just list some references. And as I mentioned, why the Nobel Prize? Why this Nobel Prize given to the Shapley? It's because ultimate question for man. As I mentioned, if your girlfriend asks you why you love her, the answer you are on the top of the list. How you define it, up to you.
Then there is another problem may arise that you have more prefer. So not in the number of. So you have when our friend asks, you have more preferred on. Then there is another problem arise.
I know, but true. Yeah. See, the next question is that what is the length of your preference list?
Yeah. In the preference list, maybe the answer should be one preference.
Yeah. You must be married. Anyway, here is the reference, and you can see that there are many kind of paper, and recently for matching theory, and it can combine with many different things. So I feel that the matching is a good kind of solution that you can combine with many things, and the complexity is low. But pay attention to two things. First one, the GS algorithm is very general. Everything is a kind of a variation of GS algorithm. But I think the major two things is that with the external effect, you need to swap. With a dynamic, you don't need to run the GS algorithm again. You only need to part of it, which is RVV algorithm. And also beyond, and when you do the matching, you have a different classification. And then think about your resources. Think about your situation. Is it one side or two side? For both sides, do they have a kind of a preference list or not? Then you fall into the different category. For different category, they have different algorithm. And moreover, they might be more than two sides. You might have three sides. Men prefer woman, woman prefer dog. Okay, this is typically good for this cloud computing. Cloud computing, sometimes you have multiple layers. And then in this case, so think about what is your scenario, and then try to find the corresponding fitting matching game, and then try to solve it. So this is matching is a kind of a very big variety. They have many different algorithms. So that's the reason, okay, matching is very popular recently for resource allocation because it's a very variety and it fits many situations. So any question? So if not, let's come back at 10:30, and then we talk about contract theory. So basically, okay, that's very important. I mean, not only for students, but also for you want to be a professor. For student, you try to think how to fool the professor, and so professor how to make sure they are not get fooled. And this is contract theory. Okay.